Hello, today we're going to evaluate using sacred geometry circles, and from that series of sacred geometry circles, we're going to find that we can find several square roots and relationships relating to the golden number phi and right triangles that relate to it as well. Let's go to our work surface here, and what we're going to do today is find several relationships between using just simple instruments like a compass and a pen, straight edge like this here, and just our brains. We're going to find several very interesting relationships between the circles and what seem to be totally unrelated concepts in trigonometry and triangle geometry. In fact, what we're going to find today is a very interesting relationship between square roots and sacred geometry. And we're going to do it using like I said, simple tools. We don't even need a calculator. We'll use one at some point in this discussion to identify a decimal expansion of a number, but we don't really need it. All of this is going to be done using just simple tools like, say, we'll put a pen here and maybe a very simple compass right here, and then all you need is a straight edge. So we'll get started with that. Let's clear our workspace here and begin with just our compass. What you want to do is set your compass to a very narrow radius. If I'm using my hand as a measurement, something like a little bit less than an inch is what you want. And the only reason you really need to do this is because when you start drawing circles, they get pretty big pretty quickly. We don't want the circles to go off the page. So I'll start with a circle here, and this will represent a circle of radius 1. Just draw it in. All right. Now, some people start with what's called a construction line, where they use before they were to draw this circle, they would have made a straight line with a straight edge. But I like to see the straightness, the verticality, and horizontal nature of the drawing that I'm making emerge from the sacred geometry and not the other way around. So first, I'm just going to mark a point. It can be anywhere on the circle, but I'm going to choose what looks like up to me. And I'm going to place my compass point on the edge of the circle, and I'm just going to draw another circle. Each one of these circles has the same radius, and that is 1. And if we stopped right here, we'd have something to meditate on for quite a while. This is a vesica Pisces. Looks like a Venn diagram, if you've ever seen one. But this is a vesica Pisces. If I circumambulate around this original circle, I will form something called the germ of life. And that's what we need in order to find vertical and horizontal axes in this image. And you'll see once I draw it in that I have to turn my paper slightly to match the true nature of up and down and left and right according to the sacred geometry. So place your compass point at the intersection of those two circles and just rotate your compass around the original circle. That's why I said circumambulation. Just walk around the original circle and you will form beautiful flower shape in the center of your image called the germ of life, the seed of life. the last circle here. And there we have it. Beautiful, harmonious, geometric shape formed with circles that we're calling the germ or the seed of life. Okay, I can now find what up is and down is and left and right. And the way I can do that is just by identifying points on this picture. Let's start with this point here and this bottom of this little flower petal here. And what we'll do is we'll line our straight edge up with the points. What I like to do is first I like to put my pencil down, and then I like to bring my straight edge in. That way I don't mess up. The bottom's going to pass through that point there. So I'll just draw a vertical line. Okay. Now, what about horizontal? Well, these points appear to be exactly opposite one another. These are two vesicas right here. So I will do the same thing for the horizontal line. And now, as you see, I have to rotate my paper. Ah, that's better. That's now vertical and horizontal. This is a perfect 90-degree angle right here, and that will become important to us as we proceed. Now, the first thing we'd like to note is that this distance from the origin point, which we can call 0, to the edge of the first circle we drew, this distance right here, that's unit of 1. Okay, so for the proportions of the different shapes we're going to draw throughout this tutorial, this is 1. You need to write it in. This is 1 right here. 1. Well, the first interesting fact we'll notice is that if this is 1, then this vertical axis from the origin point to the top of the first circle we drew is also 1. Okay, so I'll write that in, 1. There is a special right triangle whose angles are 45 degrees, and 90 degrees, where the relationships of the sides are 1, 1, square root of 2. That's base of 1, height of 1, hypotenuse of square root of 2. So I can draw in a hypotenuse right here, and I'll draw it in with a pencil. And that hypotenuse has a length of square root 2. So I'll draw that in. This is the square root of 2 right here, this hypotenuse. Very interesting. What else can we find in this image? Well, there are more things in heaven and earth than are dreamt of in our philosophy. And there are more things in this picture than seem apparent at first glance. What I'm going to do is expand the radius of my compass to be the diameter of the original circle. So if my original radius was 1, that's 2. 1 plus 1. Place your compass point on the edge of the first circle where it meets the horizontal axis that you drew. And your pencil lead should come down right on the other edge of the circle. Now, make a big circle that inscribes the initial circle. All right? Now, flip your compass around, and you're going to do the same thing by placing your compass point on the other end of the circle where it crosses the horizontal axis. And you'll see that it hits the circle on the other side. And so now you're going to inscribe another circle. All right? This point where the two circles meet on the vertical axis is a distance from the origin of square root 3. Now wait a minute, you say, how do you know that? Well, we can prove it using the Pythagorean theorem, but remember there's another special right triangle. There's a 30, 60, 90 right triangle, 30 degrees, 60 degrees, 90 degrees. Another special right triangle, and in that right triangle, the side ratios are, if the base is 1 and the hypotenuse is 2, then the height is the square root of 3. So if we're going to make a triangle here with a height of square root 3, then this hypotenuse is equal to 2. So let me just lightly draw in. That's the right triangle we're making. This is a 30-degree angle right here, 60-degree angle right here, and that's 90 degrees. So if this base is 1, this hypotenuse is 2. We won't write that in because that's not what we're really after here. This is a video, after all, about square roots. And this height is equal to the square root of 3. This is the square root of 3. Pretty fascinating so far. But there, if you can believe it, there's still yet more to discover in this image. So keeping my compass equal to the diameter of the first circle, which would be compass radius set to 2, I'm going to place my compass point at the origin, right there. And if I then draw another circle, you'll notice that it completely encompasses the first image that I drew, that germ or seed of life. This point right here is distance from the origin of 2, because there's radius 1, and there's radius 1, so that's 2. If this is 1, if the base is 1, and the height is 2, there's another special right triangle not often discussed that says if the base is 1 and the height is 2, the hypotenuse of that triangle is equal to the square root of 5. 5, number 5, square root of 5. So I'll draw that in. This hypotenuse is equal to the square root of 5. All right, that's fascinating that we know that. So we have very interesting relationships emerging already. Just from, you notice we have not used the calculator. We've not referred to trig tables. We haven't had to do right angle trigonometry or use a protractor. We've just used the sacred geometry, and we have found 1, 2, square root 2, square root 3, and square root 5. But we are not finished, ladies and gentlemen, because we are now about to enter the upside down world of phi. And I didn't say 5 just now, I said phi, P-H-I, a Greek letter. This is phi, and this is represented by the Greek letter phi. Right? Sometimes you see this written like this, be written like this. Right? Either way, it is phi. Now this is actually a number. It's an irrational number that goes on for infinity, and it never repeats itself. So any decimal expression that I give for this will be necessarily incomplete. So what I'm going to write down is the exact expression for it. The rational expression for phi is 1 plus the square root of 5 divided by 2. This is the golden number. So, if I wanted to evaluate this out a little bit and show you what this number was, I could take square root of 5 plus 1 and then divide by 2, and it would give me this decimal approximation. I'm going to leave that there. I'm not going to write it down because where you set your float point on your calculator will produce a longer and possibly different answer, but you'll all start with 1.61803398874, then it will just go on and on. But I want to point out that this is a number. Phi is a number. It's not a variable. Because when we start doing the Pythagorean theorem, it's easy to confuse this with the letter y. And you start to think of it as a variable, but it's a number. Just like pi, 3.14, it's a number, just represented by a symbol, which is a Greek letter. Well, I claim that we can find this in our picture using sacred geometry. Let's see exactly what is this expression telling me to do. It's telling me to add 1 to the square root of 5 and then divide that by 2. Well, let's do it visually and see if we can't find out something interesting. If I look at my picture, I do have 1. There's 1 right there. And I do have the square root of 5. The square root of 5 is right there. So here's what I can do. I can set my compass equal to this distance of square root 5. It's like that. And if I place my point where at distance 1 from the origin, and I draw a circle starting at square root with a radius square root 5, draw that circle in very lightly. Then the place where that new circle passed the horizontal axis is the square root of 5. Okay, that's that distance, and the distance from the origin is 1 plus the square root of 5. So here's what I'll show it. This point right here to this point right here is square root 5. Right, this is the square root of 5. So it says here that phi is equal to 1 plus the square root of 5 over 2. Well, let's proceed to make our compass equal to this distance 1 plus square root 5. All right? Oh, we can flip the compass around to where the pencil lead is where 1 plus square root of 5 is. That's distance 1 plus distance square root 5. And I've made it 1 plus square root 5. That's the distance of the compass. So if I rotate a circle around this, it'll have a radius of 1 plus square root 5. And that's exactly, ladies and gentlemen, what we're going to do. Place your compass point at the origin and rotate a circle from, make sure you set your point correctly. Your pencil lead may require you to make some minor adjustments, and make a big circle all the way around. That circle has a radius of 1 plus square root 5, because you can actually see that right there. That's the radius, 1 plus square root 5. If I flip it around, 1 plus square root 5. All right. Now, if I want to go back to my phi equation, my phi formula, it's 1 plus square root 5 divided by 2. So how do I divide this in half? Well, we can use circles. We can use a property of circles, and we can bisect the circle if we place our compass point at the end, at the edge of that big circle we just drew, at the end of this 1 plus square root 5, and we leave it the same radius of 1 plus square root 5, and I place that compass point right at the edge of that circle on the horizontal axis, and I draw another big circle. You'll see that these two huge circles form an enormous vesica right here. And when we were finding horizontal and vertical lines earlier, we noted that we could line up the points of the vesica to find a vertical line. So I'll take the points where these two circles meet, and if I lay my straight edge there and draw a soft vertical line right through the horizontal axis, it will pass through phi. Okay, let me make that a little bit darker. Okay, this point right here is phi. This is phi. And I actually would like to color that in with red because it's really important. That point right there is phi. So this distance to the origin is phi. Very interesting that that's there, just with circles. But we're not done, because there's even something more fascinating at play here. There is another special right triangle that is called the golden triangle, because phi is the golden number. It's also called Kepler's triangle, after Johannes Kepler. It is absolutely fascinating, and it has the special relationship that says if the base is 1 and the hypotenuse of the triangle is phi, then the height of the right triangle is the square root of phi. Well, let's see if we can figure that out. Let's set our compass equal to phi, now that we know what phi is. Okay, that looks about right. I might have to make a slight adjustment when I put it down. And what I want to do, I need to figure out where to place the pointing end of my compass. I want the base of my triangle to be 1, and I want the hypotenuse to be phi. So if I place my point on the horizontal axis at distance 1 on the horizontal axis, and I rotate it around, and I make a little mark on the vertical axis, okay, and then I flip my compass over and go over to the left of the origin point, distance 1, put my compass point right there, and I make another little cross mark. I've made a kind of X, see, very lightly, an X. That point on the vertical axis, this point, distance of this point to the origin is the square root of phi. So for this, just use a straight edge. This distance right here is the square root of phi. And the hypotenuse of the triangle, if I form the triangle, which I will, place my pencil lead at square root phi distance on the vertical axis from the origin point, and I bring my pencil down to 1, where 1 is on the horizontal axis, I'll form a hypotenuse of this Kepler triangle or golden triangle. That hypotenuse has a length of phi. Right? We will show this with the Pythagorean theorem in just a moment. The height of the triangle is the square root of phi, and the base of the triangle is equal to 1. So it's 1 square root phi phi. Now, you might be scratching your head and saying, is that really true? Because that seems pretty remarkable. And it is really, really remarkable. What's even more remarkable is that I'm going to try to prove it right now using a pen. So I can't erase any mistakes. Let's hope I don't make any. All right. Before we use the Pythagorean theorem, it is important to note one special property. Suppose I'll write this in the red pencil, of phi. Phi is the only number, ladies and gentlemen, that has this property. Phi squared is equal to phi plus 1. It seems very simple, but that's very profound. Phi plus 1 is equal to phi squared. If you don't believe me, check this out. Let me start with my exact formula. There's our phi number. Okay? Now let me add 1 to it. It equals 2.61803988874. Now, if I hit this square root number, it should go back to being the number 1.618033889. It should literally be this number minus 1. Okay? There it is. Plus 1 equals 2.618. Hit the square root button. We're back to our number. It never changes. I add 1 again, and then hit square root, add 1, hit square root. It's the same number over and over again. So it has that very special relationship, and we're going to use that relationship here when we do our Pythagorean formula. So according to Pythagoras, the genius of ancient Greece, a squared plus b squared is equal to c squared. What does that mean? It means that the sum of the squares of the base and the height of a triangle, a right triangle, is equal to the square of the hypotenuse. Well, that's still not very clear to someone with my limited intelligence. So what I'll do is say if a is 1, we'll call 1a. And let's say we don't know the height. We think the height is the square root of phi, but we really don't know. So let's leave that alone and prove it. What we're saying is that's equal to the hypotenuse, which we were fairly certain is phi. We found it with our compass. We found that using circles. We're pretty clear on that. So I know C and I know A. I don't want to find B. So let's put in what we know. This is 1 squared, okay, base of 1 plus height of B squared equals hypotenuse of phi squared. Okay, this is where I was saying be careful. This is not y squared, it's phi squared. That's a number squared. Remember, phi squared is equal to phi plus 1. So what I want to do is get b squared by itself. So I'll subtract out 1 squared from both sides. So what I'll write is b squared is equal to phi squared minus 1 squared. Now here you might be tempted to take the square root of b squared and the square root of phi squared minus 1 squared, and that would get you into a lot of trouble. Would get you into some trouble. So let me do this. Is it legal, if phi squared is equal to phi plus 1, is it legal for me to substitute that in for phi squared, phi plus 1? Yes, it is. It is legal. That's a little trick, and that trick's going to be helpful. So b squared is now equal to, we're going to substitute in phi plus 1 for phi squared, since we proved on the calculator that that's what it equals. We're going to say phi plus 1 and then minus 1 squared. Well, 1 squared is 1. So I'll say minus 1. Well, 1 minus 1 is 0. So b squared equals phi, which means that if I take the square root of both sides, then what I have is b squared, or b rather, equals the square root of phi. So I just proved that the height of this golden triangle right here is indeed square root phi. And that's just remarkable. It's remarkable that Pythagoras knew that. I assume that he knew it. It's certainly true that Kepler knew it. But what's even more remarkable is that there was a whole group of people that predated Pythagoras and Kepler by thousands of years, and those were, ladies and gentlemen, the ancient Egyptian pyramid builders. So the Great Pyramid at Giza has a phi relationship that is exactly equal to this. The height of the Great Pyramid is a multiple of the square root of phi. The sides of the Great Pyramid are multiples of phi, and the base is a multiple of 1 plus 1. Well, we're going to make a big triangle here in a moment. But the Great Pyramid of Giza essentially takes this Kepler triangle and reflects it, and that's the face of one of the sides of the Great Pyramid. So why don't we do that too and build the Great Pyramid? And that will be a good way to conclude the video. What I'll do, since I know that the base is 1, that half the Great Pyramid's face is base 1, I'll just go over here and draw another line from height square root phi down to base 1 on the left side of my vertical axis. And now I have an isosceles triangle where both of the hypotenuse of the sides are equal to phi, and both of the bases of these right triangles are equal to 1. So this whole base is 2. The height is the square root of phi, and the sides are both phi. So what we'll do is shade this in and just kind of meditate on what we've accomplished. In this simple graph, which did not require a calculator, I only used a calculator to show you that I wasn't lying to you, but we didn't need it. Using nothing but circles, a compass and a straight edge and a pencil. That's remarkable. I used a pen to make it stand out more for the camera. You don't need that. We have found some truly remarkable mathematical information. We have found the square root of 2, the square root of 3, the square root of 5, phi, the golden number, and the square root of the golden number, square root phi. All of that in the time it takes to watch a half-hour sitcom. We have done sacred geometry and learned an incredible amount about how triangles work and how circles correlate with triangles in sacred geometry, even to produce something as complex and awe-inspiring as the Great Pyramid of Giza, which we did. So you do this yourself. I would tell everyone that you know that you are now a great pyramid builder. You have been inducted into the ancient tradition of this sacred knowledge, and I hope that you take what you learned in this video and continue learning about sacred geometry, because I am a very poor teacher. I'm not a smart person, and you are definitely smarter than I am. So keep searching on YouTube for tutorials on sacred geometry. Be careful who you listen to. I will tell you there's one YouTube producer named SGD. I won't write it. SGD, it stands for Sacred Geometry Decoded. And he does very good tutorials on sacred geometry that will help you. If you want to look at my other videos, I expand on this a little bit, but we will bring the video to a close there. And I want to thank you for watching. I think this is quite fascinating that we're able to find all of this information in such a simple image using nothing but a compass, a straight edge, pencil, pen, a couple of colored pencils. Very interesting that we can find all of that. So thank you for watching, and please like and subscribe.